Good morning, everyone. Today, I would like to share with you this article called Rapid Production and Recovery of Cell Spheroids by Automated Droplet Microfluidics. The authors recognize that the future of life science is linked to automation and microfluidics, and they used a robot, a liquid handling robot, to produce cell spheroids at high throughput. They do it scaffold-free, and they use a droplet generating microfluidic chip and interface it with a pipetting tip. So let's see how it works. So as you can see here, the liquid handling robot has this micropipetting, and it's going to move it through all the racks that you see here. So they built a microfluidic chip made with PMMA, and they also did a 3D printed reservoir, as you can see here in C figure. And here we see all the stages of the droplet generation. So here, first filling up droplet generator. After that, after 12 minutes, the spheroid are going to start formating, and then it's the cell incubation, then spheroid recovery, and spheroid relocation. So let's see how the design is made. Here you see the design, which was engraved in PMMA polymer, and here you see the 3D printed reservoirs for the continuous phase and for the dispersed phase. And you see that the tip has this O-ring, which is going to make it possible for air and liquid tight. So this micropipetting is going to be the negative pressure source. And because it's airtight, they won't need pumps, syringe pumps, or pressure controllers. That's why the cost of this platform is reduced. So here we see how it's assembled, and when the droplets are generated, the cells are going to sediment, and after 16 hours, spheroids are going to be formed. Here we see the distribution of the sizes of the micro droplets that they obtain. As you can see, the diameter is 290 microns, and it's a monodisperse distribution because the variation coefficient is less than 5%. It's just 1.7%. And finally, you see here some images of the flow focusing architecture of the micro device, where the continuous and dispersed phase are going to encounter. So here we see a very nice pictures of the spheroid formation, and also after 16 hours, we see the how the cells have aggregated into spheroids. They also measure the cell viability, cells in spheroids, the viability 90% approximately, and this is cells prior to encapsulation, so it hasn't disturbed cell viability. And here we see some markers in order to check the cell viability. You see in DAPI the blue staining, and in red the dead cells, and in green the cells that are alive. Okay, after that they recover the spheroids, and they do it with in some ways, but the one that is the most interesting one is with this membrane. So they use a membrane-based sample recovery process based on physical separation of two phases by an oil-attracting, this is an oleophilic membrane, and it's hydrophobic. So it's made with polytetrafluoroethylene. And here in this schematic, you see that the oil is going to be separated in this membrane, and the emulsion is going to be recovered. So after the separation of the oil, we have just the spheroids with the inside the droplets and over the PTFE membrane. That's how they recover. And they are able to produce a two 2 times 10 to the 6 spheroids in 84 hours. So that's very impressive because it's all this automatic and operator-free. And they also characterize the cell spheroid that they produce by the circularity. So they use the circularity, they use the measure command in ImageJ to compute the circularity of the spheroids using this formula. And because they are not perfect spheres, and it also depends on the cell line, and they compare the different values of circularity that they obtain from each cell line, and they explain this difference because the cells can be packed in different ways. It also depends on how they sediment inside the droplet. So this is very interesting finding, and it also really enhances reproducibility, which is the success in lab work. Okay, thank you very much.